I've been working here since past years. So hearty welcome to all of you in this session regarding introduction to machine learning. So we have been hearing about IoT since past 3-4 days, and we know that the essence of uh, IoT is connected environment and sharing of information, data collection. Okay. In one article recently I was reading, so one of the enabling factor for the modern day IoT technology is data acquisition, storage, transfer, and communication between the different things within codes. So this first session will be about machine learning. There are many concepts that we should need to take care of while doing machine learning, and we'll see that when we have to get good outcomes from machine learning, then we need to work on the data that we acquire, because that's what is going to give performance to the IoT system we conceive of. There have been so many embedded hardware technologies also introduced, like we have Node MCU, Arduino, and Raspberry Pi, and these kind of things. And these things are being used. There are systems, high performing systems, and different architectures are being introduced, and all of them are generating data. So when we deal with data, if you're not dealing with that properly, then we cannot get any good use out of that. So with keeping these points in mind, I am going to talk something on machine learning in this presentation. So let me share the screen. By the way, am I audible, Maya? Sound is proper?
Yes, sir, you are audible, sir.
Okay. Loudness mapping. Okay. Sharing. So is it coming, Maya?
Yes, it's visible, sir. It's coming.
Visible. Okay. So thank you very much. Um, Introduction to machine learning. So first of all, this confusion is there many times, and some recent articles on web I was reading some 2 years back. So people say that no, AI is machine learning, or AI and machine learning are separate, and things like that. But to clarify, machine learning is basically a it is an enabling factor. AI basically is realized through the help of several AI techniques. We say, like in formal AI texts, we find that they discuss about what's an AI technique. So, starting from the simple idea of using search algorithms that use knowledge to eventually come up with a good solution for a given problem that is formulated in a standard manner. So there are other AI techniques that are also used. So for every AI technique, we have to give a proper computational representation of the input data and the domain knowledge in a manner so that that can be consumed by the AI technique. So the data will be processed based on the kind of representation of the domain knowledge that we give. And there may be different types of knowledge representation techniques. Like in case of AI, we can have simple rule-based knowledge representation and followed by use of search algorithms with or without the heuristics. So if we are using heuristics, then we are doing informed search. If you are using search algorithm for the consuming the rules for starting with the initial problem configuration to eventually try to achieve the goal configuration. We cannot always guarantee to get a goal in case of using search, especially for bigger problems. Say, for example, the traveling salesperson problem. Then there can be other knowledge representation mechanisms that may use logic. So we know that there are two branches in logic, very popular one, conditional logic, another is predicate logic. So we find that for practical purposes, predicate logic is used, and that too because of so many formalisms and symbolisms in the first order predicate logic also, we eventually end up to use clause form, which forms the very basis of uh, these languages like Lisp and Prolog, which are very much used for A applications, where knowledge representation is in the form of logic. And we do inferencing, and there are different rules like modus ponens, modus tollens, and things like that. So sometimes fuzzy logic is also these days being used, combination of this kind of logical rules with fuzzy logic, that is also done. Then we also use probabilistic knowledge representation, and then for them also we have like reasoning mechanisms. So there also we say that we are having AI techniques. Then we have knowledge which do not like follow a very systematic um, like organization. So we have different knowledge items, and we do not know exactly or cannot explain very properly how to represent that. So for such kind of thing, we eventually end up representing this kind of knowledge using some numerical representation. Say for example, image data. So that is represented using numbers we know. Then something that the neural networks learn. So then there the data is also represented in numerical fashion and things like that. And then the processing logic is also numerical. So machine learning is basically then something what is a collection of so many techniques, supervised, unsupervised, and semi-supervised, as we'll see. So which all are like AI techniques. So machine learning is basically a branch of study of AI. So we should not confuse that AI is separate from ML. In fact, ML, one of the promising ML technology is deep learning, which is can be seen as a subset of machine learning, and machine learning comes within the realm of AI. So formal comments on machine learning. Machine learning is the field of study which gives the computers the ability to learn without being instructed. This is a famous comment by Arthur Samuels. So what is the whole idea? The whole idea is that we do not want to write hard-coded programs. Say for example, if you have to do some analysis of accelerometer data, then robotic system can walk or run depending on the response to be provided against the accelerator input data. So we can write a custom-made program, and then we can run it and get the desired output. But then that is not the goal. We have to then do it every time again and again. So instead of that, if we develop some mechanism by which the computers on their own can develop the ability to learn from the input data they get, and we do not do explicit programming, and then take some actions. So this is what was the idea that was presented way back in 1959. There's a big history of AI which started, I think, with the introduction of the first model of artificial neuron by Rosenblatt and Pitts. Now, this McCulloch and Pitts, followed by Rosenblatt's perceptron model, Wittdorf model, things like that, Adalin model. So Minsky and Pepper's neuron model. So this was like way back, some 60, 70 years back, these things were introduced. So a computer program, this is another comment, a computer program is said to learn from experience with respect to some class of task T and performance measure P. If its performance at tasks in T are as measured by P improves with experience E. So let us try to understand this comment. So we have a computer program, we designed it, and let's say the experience of this program as E, capital E, and we have certain tasks which we put under one class T, which the computer program has to carry out. There are different tasks under class T, and when the computer program does those or performs those tasks under the class T, so then the performance of the computer program is measured using a performance measure, say P. And if its performance in performing the task under class T as measured by P improves with the analysis of the input due to the experience E, then we say that the computer program is learning. So this was the formal comment by Tom Michels, 1997. Now the question arises is that why we need to learn using computers? So I put some points here. Learning may be needed, in fact, when we to customize and tune themselves to individual users. Say, for example, we want our response against user biometrics. So user biometrics is like different for different individuals. So at an individual level, the supporting computer program that is given with the particular individual for analysis and like output of response against the measurements of the biometrics, that has to be suitable with respect to that individual. It will be different for different individuals. So in that case, learning is required. We cannot write a generic solution that will take care of user biometrics of a certain category for different persons. Not possible. So learning is required in such cases. We are not able to explain our perceptive abilities, like how we understand or recognize speech. So we as human beings, we are not able to explain our perceptive abilities, but we at the same time want the machines to be able to recognize speech. So in that case, we will need learning. The machine can be fed in data, and then from that, the machine can try to figure out that how this like data is giving some message with respect to recognition of speeches from different persons. Say, if you are recognizing speeches of different persons, or say something else related to speech recognition, like identifying the topics spoken in the speech. So there can be different analytics, but the idea is recognition. So we ourselves do not know that how we are able to recognize speech. It's a very practical example I have taken. So we cannot explain to the computers how will you write a program. So in that case also, learning is a good solution. Then in a particular domain, say a problem, we as humans have no expertise only. There is no human expertise existing. So say for example that a very new task is started related to um, uh, let's say, taking example, say hadron collider. So this is a project that was introduced once to the world, and now in relation to that we want some AI solution. So how much human expertise is available? Practically very less, nothing. Such a thing was never created before. So in that case we have no domain knowledge only. So how to put up things, okay, for writing a program in a computer so that some AI technique can be, as I said earlier, AI technique can be executed with respect to some problems related to, say, this Hadron Collider project. So wherein we have no knowledge existing. So like we are sending satellites outside. So outside, what factors are affecting the life expectancy of these like satellites? So So there is no human expertise or human knowledge available for that. So in that case, the better idea would be that with those satellites only we equip sensors, and then data is sensed, analyzed, and based on that, there only some processing can be done, and in the base station on Earth, we may be sent response regarding the status of the satellite, because humans cannot go there and acquire knowledge regarding the effects that happen on the satellite due to the different factors there in the space where the satellite is actually working. Then we also will need learning in situations wherein the computational solution that we are going to present is to change with respect to time, especially with time series data. So the time factor is important, and with time the logic of the solution has to change. So definitely we can then in that case take help of learning from the input data, and accordingly the program can adapt and process the input data and give different solutions with respect to the time. Then, so the counterpoint that I have shown here is that when we are learning, we won't prepare a computational mechanism to learn to calculate parallel processing. So if we have to calculate payroll and process that, we do not need learning in that case. Now, this is a distinction between traditional programming-based solution and machine learning algorithm-based solution. So suppose if we have input from sensors, etc., so hard-coded computer program we write, as I said earlier, this example also, that it has to produce output that whether based on the input received from the sensor, there should be the response that the robot should run or walk. So you can write a program for that, but then we have to do it every time, so that we don't want. On the contrary, if we write a like machine learning implementation using some ML model, say neural network or say logistic regression or random forest based model, and the sensor data is used as the knowledge supplier, ingestion, preprocessing, and then the ML algorithm does training of the model, and finally presents the output. So here the rules are learned. So means that what rules are implied by the input data, so they are now known, and with change in data, periodically the model performance can be retuned. Sometimes we say that there may be some kind of model decay. So if there is some model decay, so in that case, periodically we can again retrain a particular, like ML-based implementation system, and then again, it can continue. But if we have to write programs, so definitely that is going to be a very hard task. So this is the difference between programming-based solution and machine learning-based solution. So there are many use cases for machine learning. So I've listed many that I was, like seeing through in the past many days. These are very recent ones, and in these like cases, ML is heavily being used these days. In telecommunication, we are using in like environmental monitoring, especially air quality has become a big trouble. So the measurement of the ppm concentration and other aspects related to the quality of air we breathe. In retail marketing, the customer review analytics and related things are done with respect to use of so many ML algorithms, and then it is also used in security and surveillance. Like we see that there are so many systems being developed these days for monitoring videos that come through CCTVs, and especially in an IoT environment, the video footages can be like resulting in huge amount of data also. So that is in fact a good area of research. So there also we see the use of ML. Then in structural health monitoring, There are like a lot of implications of AI in healthcare. We are using AI, and in general, environmental monitoring related to waste and related to the like the water bodies and then the vegetation. So people are applying ML techniques, health monitoring in general. So intelligent transportation. This health monitoring is with respect to use of wearables, and then intelligent transportation. So we know that uh, in case of this mm, remote monitoring, one nice example is smart homes and monitoring patients and aged persons remotely via IoT network. So ML is used. Then in the domain of security of energy, especially like for nuclear power points and other like sources of energy, especially in the government like enterprises dealing with the different ministries of energy and the relevant security AI aspects. ML is being used. So in supply chain management, it is being used. Location and tracking related data can be used for performing ML. So many like real life things are there. So this is a diagrammatic representation and courtesies of all these images to Google. So we see that there are other applications uh, of AI with respect to virtual assistants, and we see that these are like popular trend that in many websites we see that they have chatbot support, chatting support. So we see that especially some popular examples are Siri, Alexa, and then Cortana, and application of AI. This spam is real problem. In the last few months, we realize like predictive price like analysis and when there is another thing, misuse of offers. This was a recent problem I was studying, that many times what happens is that some online like e-commerce website gives offers and people keep changing email IDs, and then they try to get like the same discount again and again through different email IDs. So they are by analyzing the buying trend and the payment trend of the users registering in the e-commerce website via different user credentials. So some analysis can be done and such kind of fraud behavior can be avoided. It is also possible to apply ML for customer support and for even recommending good advertisements and things like that. And in transport, especially in IoT scenario, we see that like we have this different vehicles communicating with each other. Just 2 days back, we are hearing about machines communicating with each other through sensors. So there, a lot of data is generated, and based on that, the safety monitoring of the vehicles and the traffic in general can be taken care of. Also, ML has found this application. Then in drug discovery, definitely in past decade, like ML has found good applications, and in disease diagnosis, especially in diagnosis of diseases through analysis of images using deep learning and other medical related scans, like the output obtained from different scan technologies like PET, MRI, CT scan, and things like that. So for them, ML have been used, and for like some surgeries also, robotics technology have been used. So there also ML is used. Then in So another related and in like stock market, so that there also it is used. So there are a lot of applications. So what are the different types of ML? So we have basically three broad categories. Supervised learning, that is mainly related to classification and regression, and the second one is unsupervised learning, and the third one is reinforcement learning. In case of supervised learning, the word itself tells things are straightforward and clear. We will have data, and we will know something about the data very clearly. Okay, and based on the good information regarding the nature of data that we have, we can do some training, and then unknown data can be judged upon, and then depending on the nature of the problem, whether it's a classification problem or regression problem, so we can do stuff. Actually, uh, uh, there is a subtle difference between classification and regression, but the activities carried on for these two have a lot of similarity. In case of unsupervised learning, there is no teacher, and like it is compared to supervised learning less used, but it is used. Whereas in case of reinforcement learning, the very word reinforcement means that first allow something and then give some judgment whether things were correct or incorrect. So that kind of learning is also used. So like for example, we have this TD lambda and this kind of algorithm, SARSA and things like that. So these are examples related to reinforcement learning. And this is another very important aspect related to doing machine learning when we have data in our hand. So definitely in a connected environment, and we can like always remain connected to online data repository, and pull out data from there and keep feeding to the machine learning model for its training and things like that. So that is like the online mode of doing machine learning. But we can also have machine learning models that suppose we develop a neural network. What we do is that we once train it, say 2 months back with good amount of data, giving it servers, can't we use data with us? Even if we do supervised learning, of the train with following certain like learning algorithm for a particular for a particular time, it was offline, it was used, and then again it can be trained in batches, and then sometimes there, if there is model decay, definitely we have to do. So this is another view that we should keep in mind, that one can be online way, another can be offline or in batches. We can like incrementally improve the quality of or performance of the ML. Then this is a good cheat sheet figure related to choice of ML type, machine learning type. So we have already seen that there are three types of machine learning algorithms. Voice is breaking. Maya, voice is breaking. Dalingma?
Yes, sorry. Now it was breaking before.
Now it's okay.
Now it is okay.
Okay. Yeah, certainly I thought to see. That's why. So there are these three categories: unsupervised, semi-supervised, and supervised, and some like relevant tasks are also mentioned here. For reinforcement learning, if you see, that is very much popular in case of game AI. So there are in fact different categories of tasks. Okay, some are mission critical tasks, some are not so critical, and things like games. So they are not very critical, and like in that case, reinforcement learning definitely can be used. So in that sense. But suppose if we have to like use ML for some system that is related to life and death, suppose in some medical system wherein the report has to come within certain hours. So in that case, we usually go for supervised learning. So then there are some more examples like skill acquisition. Now, this is a different kind of problem. So here we cannot beforehand understand like what skills some employee have. It's a different and hard task. So here we cannot have some like available data to do supervised learning. So there may be need of a lot of brainstorming with a lot of psychologists and things, people like that who can act as domain experts, and something may be developed. So in case of like semi-supervised learning or reinforcement learning, some amount of data we somehow can get, but we cannot get too much amount of data. So that's why skill acquisition is being grouped here. Whereas for like robot navigation also, uh, suppose uh, we want to do like supervised learning, again we will need a lot of data. So in these kind of problems also, sometimes to avoid like too much of training with too much of data, we go for a choice of reinforcement learning. So like very nice problem examples are given here, and each problem example has like associated with it different philosophical concept based on which one of the three types of machine learning like can be selected. Then in real time decisions also, reinforcement learning is used, because like the data here is having the nature of like changing with time. So suppose something has to be predicted within a certain time. Suppose the chance of landslide. So if it is predicted after the landslide occurs, then there is no meaning of that. So suppose some video surveillance is being done. So if within a certain time, the persons who come, they are not identified as trespassers or not. Okay, in real time we don't get the response. So that is of no use. So there, if we wait for the good amount of time to be spent on doing supervised learning, and then we do the like activity of recognition, so we cannot afford to wait for so much time. So reinforcement learning can be used there. Then in case of supervised learning, we see there is classification, there is regression. There are two broad categories. So for classification, yeah, in identity fraud detection, image classification, customer retention, and diagnostic. Okay, good examples are given. So we are assuming that we are doing it in a like offline manner. So we have like images, and we have to select some of the images for training, and then the model's performance has to be judged, and then we finally classify the unknown images. So then in such a scenario, we can afford to have supervised learning, and we can go with classification. Then customer retention. So many times organizations, they see that how the customers are leaving us or staying with us. Say for example, when Reliance Jio introduced the
Okay. Okay.
customers, they changed from other telecommunication service providers like other companies like Airtel and BSNL, and came to the Geo offer realm. So there, definitely then the other organizations would like to do some analysis based on the past historical data that regarding customer retention. just a practical example I am giving. Then in diagnostics, several kind of diagnostic activities, especially in the medical domain, classification is used. And then in like fraud detection of identity, that can be used. One example that comes in our mind is in online marketing, as I was giving the earlier example. So like person giving or introducing themselves wrongly, okay, in a e-commerce website, by stealing some say credit card information or things like that, and taking creating a different email ID, and then trying to purchase things like that. So from the purchase trend data, some fraud detection can be done. And suppose another example that comes in our mind is related to say social media profiles. So there also we can apply classification, supervised classification, if we get some data. Then in regression, we see that advertising popularity prediction and weather forecasting, market forecasting. So basically, here it's about prediction and forecasting. Whenever you have to do prediction related activities, forecast related activities, some estimation of expectation. So in that case, we go for regression. In case of unsupervised learning, there are two different categories. One is clustering, so to find underlying trends and patterns in the data. So we go for clustering. There are so many popular clustering algorithms like k-means, k-means, and things like that. And there are fuzzy versions also, like fuzzy c-means. There are other activities where also we use clustering, as it is mentioned here, recommender system and targeted marketing also. And for dimensionality reduction also, if we have very high dimensional data, we need to do some kind of dimensionality reduction. And that is also important when we need to combine features. When we do feature extraction, many times we do feature engineering, and we try to combine features also. So there also we use feature explicitization, then structure discovery, meaningful compression, and compression dimensionality reduction finds a lot of use. Like big data in terms of size, in terms of dimensionality, there are different aspects. So there also we need to reduce the size of data. So this is supervised learning. And there are two broad categories we heard: regression and classification. Basically, why? So we are actually trying to find a exact class label. In fact, the classification task also categorized as multi-class and multi-label classification also. So when we are doing regression, so the output that a particular supervised machine learning model is producing is not a class level or a one of the many levels of a class. In fact, it is a real value. Okay, as we saw example, that let's say we have to do weather forecasting. Like here we see regression weather forecasting. So if you want to predict tomorrow's temperature and the amount of rainfall, so there we can do regression analysis using some supervised machine learning model. And after the training, the model will be fed in with the possible values of input factors related to tomorrow's weather prediction. And the output of the supervised machine learning model would be expected temperature and expected rainfall quantity. So these are not class levels or one of the many levels of different classes. These are real values, real numbers. So this is one kind of activity. So second activity is classification. So we can have multi-class classification and we can have multi-level classification. And in that case, what happens? Let's say we have three sets of images. We have images of cats, we have images of horses, and we have images of camels. And the model is trained to identify cats, horses, and camels. So training. Now, if we give an unknown image of a cat, so suppose the cat class level is 1, so the output 1 here represents a class. It doesn't represent any real value. 1 here represents the cat class, say 2 represents the horse class, and 3 represents the camel class. So these will be category levels. And sometimes we see in certain problems we want to associate multiple labels to one class only. So as an example, suppose we want to associate different tags, to the same news article. Label data is available with us for different news articles. So tags and labels, many times when we write comments, so we put tag, like in case of Twitter we put tag. Now we have the tag data available, we have the input training data available. We train a model, say some machine learning model, say SVM or neural network and things like that, or RNN. And we then associate with every new news article many of the tags. So all those tags together represent one class. So that is also classification, but the only difference here is technically that just associating one quantity and sometimes associating multiple quantity or things, okay, with one class. So simple classification problem is that suppose we have 10 classes, so the different class numbers will be say 1 to 10 or say 0 to 9, depends how you number, and then the ML will predict one of those 10 numbers. And a more complicated classification scenario will be that different things related to one particular class, okay, will be outputted by the ML model. So like as I said, the example that multiple tags are to be associated with one news article through machine learning. So there also classification has to be first done. Different news articles will be first broadly classified, and then the different tags are to be associated with news articles. Then how the training happens in case of supervised learning. So we will have leveled positive and negative examples also. So many times when we try with supervised learning, we actually forget to prepare good amount of positive and negative examples. So this is what is the one of the important points related to machine learning that I want to tell with respect to IoT data analysis also, because any kind of data that we have to analyze, if you have to get good outcome of analysis for that data, then that depends on what kind of data we are using for training our ML model. So there are some good characteristics of training data. One is that, of course, we should have good amount of data. Second is that we should have good amount of labeled positive and negative examples in the training data. Then for unseen input, predict corresponding output. That is the activity that results after training. And learning is continued in case of supervised learning until we get acceptable performance in uh, in terms of different KPIs, key performance indicators. So we have to select the right performance measures. Those I have not put here because they are very popular. Like we know that there is TPR, and then this F1 precision recall, these kind of things. These are like very common fact. So based on that, we have to judge or assess the performance of the ML model after training, and until we are satisfied, okay, with a particular value of this performance, acceptable performance for the ML model, so the learning is continued like that. So we do that when we do the supervised learning, so we, like, for every phase of learning execute several epochs, we say. And if we like restart learning, so then it's a different case actually. So that is like like retraining, we can say, retraining. And like that is basically for improving the performance by comparing the different KPIs. In case of unsupervised learning, what happens is we discover hidden relations and learn about the data. So we can find interesting patterns and relationships. So there can be like what to say, simple activities based on finding similarities between pattern using some proximity measures. So some of them are popular distance measures like the Euclidean distance or Manhattan distance and things like that. Whereas there may be some use of cosine distance also in case of textual data. So like that. So here basically a lot of mathematics and statistical activities are done, and the input data that is to be clustered has to be given suitable mathematical representation. If we have input data that is already in numerical representation, if you have numerical data, no problem. But if we have non-numerical data, like if we have images, so images may be like converted to grayscale, and then there may be some normalization of the image matrices, and then there may be clustering applied. In case of text data, the different word embedding models or vectorial numerical representation models can be used. Like for text data, we can use vector space model, and there may be different this term weighting like formula that can be used. Popular one is TF-IDF. So there are so many variants available. So some of them can be used. Otherwise, these days the more popular trend for like large scale text data analytics in ideal scenario is using word embedding. So we can go for use of n-gram like word embedding modeling, or we can also use this Bojano's case character n-gram model. So this is used in case of Facebook big data, okay, analytics. So it is a very new one. In fact, this character n-gram approach was introduced, I think, in 2017. So then we can do clustering, and one of the successful like proximity measures in case of textual data represented numerically using these kind of different like word embedding techniques is cosine measure. So that we can try. So in case of unsupervised learning, broadly there are two activities possible. Clustering. So that means what? We have given data set X. So it has to be partitioned or subdivided into k disjoint subsets. And in case of association, so these are all unseen. Like, there is no teacher. We don't tell okay this computing system that how to relate the different patterns together, or how to keep them separate in different groups. Okay, the patterns in the input data. Whereas in case of association, what happens is that we have to find out some interesting relation between different data items, and save those relations. So this is also called like association rule mining. So these kind of activities are done through unsupervised learning. Here, what kind of training occurs for unsupervised learning? We assume that all examples are positive, and there are no labels, no teacher, and that's why when we do clustering on a data, there is no single correct answer. That is the idea of unsupervised learning. Then what are the practical usages of unsupervised learning? So the practical usage is that we want to derive groups. So say for example, I take some botanical data, say some flower related data, flower sepal length, sepal width, petal width, and things like that. And based on that, I have to classify the these flower related records into the different species of the flower. So there we can do the grouping. Then another like popular example may be finding like different colored regions in case of colored images. Especially clustering is also used for like medical image like processing. So suppose it's a like task of say cancer detection on some like image of say lung or some skin area, okay, for skin cancer or things like that. So they are based on the color differences of different region. Clustering may give some insight. So in this kind of task, unsupervised learning has definitely been used. Then, and like another practical user example here that I have listed is market basket analysis. So, like one example that immediately comes in our mind is that finding the purchase trend and like suggesting the different customers to purchase what with what. Like many times when we go to the Amazon website, we see that we have searched some item, immediately some suggestion is given that users who have searched it have also searched it. So that may be simply based on search data record, or there may be some data analytics done using some machine learning technique, and based on that better suggestions can be given. Say for example, somebody is using some app enabled with ML in the backend, and somebody is purchasing milk, okay, because that person does some exercise in the morning, and that person can be suggested some related edible, okay, via the like that app, okay, to purchase from the online store. So like associating different items here. So the machine representation of milk purchase data was associated with some other relevant health food product related data, and it was suggested. So in this kind of thing, like the clustering can be used because we do not know like in a very clear fashion that what are the different relations that exist between the different edibles related to see this fitness enthusiast persons food habits and things like that. So then another nice presentation here is about how do we choose to do machine learning. One is definitely that machine learning is a buzz and we want to apply ML everywhere, but that's not correct actually. That every time we have to do machine learning, and every time we can do machine learning. So first of all, we have to ask that the problem in question that is to be solved now, is it a machine learning based task? So if it is not the case, okay, then we have to try other conventional solutions. So for simpler problems, okay, definitely we need not use machine learning. As I said, that if you have to calculate payroll, we may not need, in fact we do not need to use ML. So uh, next question that we can raise to choose to do ML is it a correct ML scenario? So there are different scenarios for ML: supervised, unsupervised, semi-supervised, and then regression related, classification related. So these things you have to understand. Then, if it is no, if the answer is no, then we have to try some other scenario. If the answer is yes, then we have to see that is suitable machine learning model identified. So if that, along with that, if we don't choose the correct features, if you don't choose the correct performance evaluation metrics, then also we cannot gain much, okay, by doing machine learning. If a suitable model is identified, so then we have to ask that do we have enough data. If you don't have enough data, then even by selecting good models, like many may think that okay, deep learning is there, so I'll use deep learning and I'll always get good result. No, that may not be the case. We have to have enough data. Then is the model overly complicated? Now if we select a machine learning model, so there are relevant mathematical equations. So if the finalized model becomes too complicated because of the underlying mathematics that we decide, then also the overly complicated model may not gain, may not give us much gain in the application of ML for solving the problem in question. Then feature extraction, feature analysis in engineering is very important. If we fail to choose correct features, then we definitely cannot gain much with machine learning. Of course, in these days, with the introduction of deep learning, the task of doing feature selection has considerably reduced. Still, feature engineering remains an important, aspect. And if it is not nicely done, then even if we do machine learning, we will fail to get a good solution. And after we do machine learning, if we fail to like evaluate the performance of the machine learning model in question, then also we, because of the lack of knowledge of how to uh, like evaluate a particular machine learning model, we may not be able to like choose the right ML solution for the problem to solve. Means we have already understood that the current problem to be solved is a ML task and the scenario is correct. But if we do not evaluate the ML model that we choose for solving the problem properly, then also we cannot gain much with doing machine learning. So then for evaluation again we will need some data. So that data has to be properly chosen, like especially in case of neural network performance evaluation. Many times I have also seen some people ignore having a validation test data set. Also they do not go for manifold cross validation. So let us take a simple scenario and try to understand. Suppose I create training data with 70% of the label data, and then I train the neural network machine learning model in question. So I have trained, I execute some epochs, and then eventually what happens is that I get some accuracy, say 93, 94% accuracy. So that is not proper training. After that, okay, we say that we have to do like testing and validation. Fine. So we do that also, but then we just stop there. So it is just one time, and usually we randomly select say 70% of the data. Then how do we know that we have trained the model properly? So if we say try for k fold cross validation, then in that case what will happen is that say 10 times or 21 times, there are different values of k. Okay, we will select randomly 70% of the data of the label data for training, and then we'll train the neural network model. And for every retraining, we will do like validation and testing using validation data and test data, and then finally we can conclude the average performance from all the different performances, say 10 times the performances of 10 times of training, the performances of 21 times of trainings. This is, I also see 36 fold cross validation. So 36 times randomly we select different training data input, and then we train, and then we do validation and testing, and then finally we report the averaged performance. So that is the right way of doing like performance evaluation. And every time we are having different set of data. Of course there are challenges, I agree. There may be missing values and things like that. So those things should be taken care of before, by doing curation. Data curation is an important step in achieving good success through machine learning. So if that is not taken care of, then also there will be problem. So apart from this like choosing a good ML model algorithm, like which becomes a buzz or hit and we just hear about that, so we should not develop misconceptions. So that's why this is important that we take care of the performance evaluation, proper performance evaluation, like I gave this example, and then like the outcome of doing machine learning will be uh, proper and suitable. Now, to facilitate the use of machine learning, there are like so many organizations and market players. They are in the available in the market, and here I have like presented some information related to Azure ML, Big ML, Amazon ML, Google Prediction, IBM Watson ML. So the different algorithms that they support and the customization capabilities are also listed here. So in case of Azure ML, we see that classification, regression, clustering, anomaly detection, and recommendation, all these things are possible. And the flexibility is high, usability is high, training time is low, accuracy is high. Okay. Similarly for big ML, so those 5 activities are possible. Whereas for Amazon, these 2 activities are possible because these 2 activities are very popular in the realm of machine learning, classification and regression. So we get like predominant support for these activities uh, through different like ML vendors and players in the market. So yeah, there are some customization points also. So in case of Azure ML, like customizations are possible for the different machine learning model parameters. There is R script support also, and evaluation support also available. We can write our own script and our own models also we can to some extent deploy and evaluate their performances. Mm. Whereas in case of BigML, like we can like there is very good support for designing own models. And the programming languages support are for C Sharp, R, and Node.js. And for Amazon ML, like there is not much, okay, like parameter tuning required. That's what fewer parameters are there, and there are many plug-and-play ML models available, and we can simply put the data there and do some training out of that, and then start testing what we do by training. So based on that, we can start just testing the performance of the different models. So apart from that, other supports are not available, as you see here, like our own model deployment and some programming language support. Those things are not available. In case of Google prediction, flexibility, usability is low, training time and accuracy is medium, and the task supported the classification regression. In case of IBM Watson ML, flexibility is low, usability is high, training time is high, accuracy is high, and the different algorithms that are supported is semantic mining, hypothesis rank, and regression. These kind of things. There's one more thing, like their availability and support. So Azure ML is providing cloud-based access. On-premise access, okay, is not that strong yet. For BigML, cloud-based access and on-premise access is like sufficiently available. Means it's nicely available. In case of Amazon ML, cloud-based access is available. On-premise is not available. For all this, we can create some free accounts also. There are some try free offers also. Google prediction, cloud and on-premises support are like plus and minus. Means cloud basis is there, on-premises support is limited. For IBM Watson also it's the same. And then all these things come with a price. So this is the statistics as on 2018. So model building, Azure ML is like $1 per hour and $10 per user per month. And if we need to do retraining, as I said that we have to do some retraining to sometimes improve the performance of an already trained model. There may model decay, there may be different reasons. So that may be like costing $0.5 per thousand retraining, and then for prediction, doing prediction per thousand, $0.5 and things like that. And for computation, $2 per hour, and free usage is limited to 1,000 per month. So you can see that like the entire concept philosophy of machine learning, so it has come into business, and So similarly for big ML, it is $30 to $10,000 per month, and maximum data size for free usage is 16 MB. The data size is limited to 16 MB. For Amazon ML, prediction cost is $0.1 and 0.42 per hour for model building and computation 0.42 per hour, and free usage is not there. Okay. Recently there may be some support. This is little older statistic. Google prediction is like this, and for retraining $0.05, prediction 0.5, free usage 10,000 per month. IBM Watson ML 0.45 hour and $10 per service, prediction per 1,000 $0.5, free usage 5,000 per month and 5 hour computation only, like that. So there are something about the different types of algorithms related to machine learning. There are linear algorithms, so classification classes separated by straight line. Actually, we sometimes hear the rise and fall rise and fall of AI. So especially with respect to this classification problems and the different learning classifiers, like proposed for doing classification, computerized classification based on machine learning algorithm. So we know that famous ZOR problem, which actually inhibited the progress of machine learning in the late 1980s. So before that there were like predominant use of linear algorithms, but when the XOR problem was introduced, so it was understood that then this need was felt that we need non-linear ways of doing classification. So then again we see that later on the this Rosenblatt's perceptron model and MLP, multi-layer perceptron model, these kind of things were introduced, and again this AI based on supervised learning, especially with respect to classifiers like neural network, started to gain popularity again. Then we, in the category of linear algorithms only, find classifiers like support vector machine. So this is suitable when there is a wide gap between different this classes of data instead of just line. So we go for using hyperplanes for separation, and for doing regression, if there is a linear relation between variables and the particular label, so then linear algorithms can be used. For non-linear algorithms, the decision boundary is non-linear, and for these algorithms like decision trees, random forest, jungle divide, jungles, can be used. Why? Because they divide space into regions. In fact, ML classifiers like random forest are good for outliers also. And nonlinear algorithms category also takes care of neural networks, because neural networks can produce very nice nonlinear boundaries between the different classes. Complex and irregular boundaries can be presented through neural networks. Then there may be some special machine learning algorithms like for ordinal regression. For example, we can have ranked values. So in that case, we can use ordinal regression, and then there may be categorical data, like in terms of gender and things like that. So if you have to classify, like data based on some categorical like observations. So in that case, also we need to have some special algorithms. Then for discrete distribution, there we can have special algorithms designed for identifying Poisson discrete distribution. Then for Bayesian normal distribution of errors, like bell curve, like data having bell curve properties, we can use special machine learning algorithms. Then finally, something especially about neural networks. So neural networks are very popular these days, especially due to deep learning. So what we find is that in a neural network there will be so many nodes, and these nodes will be organized in different layers, and the different layers will have weighted connection. So a neural network can also be seen thus as a acyclic directed graph. In fact, based on the number of layers and the this type of nodes, the different neural networks can be performing differently. Like if we consider a particular node model, say uh, you know these days, like recently people started using pulse neuron models. So if in a particular neural network, instead of using the simpler uh, you know like models like Rosenblatt's perceptron model or Adelin model, or Minsky Pepper model of neuron, we use pulse neuron model. So that kind of neural network becomes a pulse neural network. There is another terminology used for that, spiking neural networks. So the network capacity depends on the the model of the node in the neural network. If we are suppose using the Rosenblatt's perceptron model to build a neural network, then what we get is a multi-layer perceptron. Multi-layer means multiple layers, and all nodes are perceptron modules. So multi-layer perceptron. But suppose if we don't use the perceptron model, we use the McCulloch-Pitts model of artificial neuron, or say Adelin model, or some other model of artificial neuron, then we get a multi-layer neural network. If you use a spiking neuron model, then we get a spiking neural network, like that. And all these nodes will be organized in layers. So definitely there has to be some input layer, and if you have to take an output from a neural network, there has to be an output layer. So these two layers will be present, and in between these two layers there can be one or more layers. So as we see below, there is one input layer and one output layer in the neural network architecture, and if there is only one in between layer, which are known as hidden layers, then such a neural network is shallow in its architecture. And the very word deep learning was introduced for the relevant neural network architectures having more than one hidden layers. So if we have two or more hidden layers between the input and output layer in a neural network, then such a neural network architecture is a deep neural network architecture, and using them we can do deep learning. That is the idea. And as we see here, these different layers can be interconnected. So there is input layer. So the number of nodes in the input layer usually usually depends on the dimensionality of the input pattern. For every pattern uh, that we supply, or every input that we supply to any ML model, there may be a related dimensionality. So in case of say any what to say, mm, say real life observation related to some sensors input, or say related to some agricultural data input, or say some disease data input, there will be some amount of dimensionality. Okay, so it's very rare to have a input layer with just one node. So typically, suppose if we talk of say sensor data, so related to suppose say some health data, so we may be sensing temperature, okay, then the blood pressure and things like that, okay, the orientation of the particular body part on which the variable is fitted and things like that. So naturally we are having more than one dimension. So each circle in the input layer is with respect to one dimension of the input record. And then what will happen in the next layer, which is between the output layer input layer, the dimensionality may increase or decrease. So and there may be many such layers in between. So these are hidden layers, and there will be like interconnections. So each node in the input layer will be connected with every node in the subsequent layer, and this is how we get a fully connected architecture in case of neural network architectures. Typically this kind of fully connected neural network architecture only is used. We don't go for more complicatedness. We don't use like special neural network architectures wherein some of the connectivities may be missing. In fact, most of the neural network architectures used throughout the world have this fully connected concept only between each node of each layer, and all the layers on the neural network in the neural network architecture will be connected, okay, fully. So every if you take any two layers, then nodes of both the layers will be connected fully like that. So if suppose some of the links are not used, then we are talking of special neural network architectures. So neural network architecture in essence is like fully connected everywhere. Okay, amidst the layers there is like full connection. So then some resources related to machine learning data, so where we can get, so we can get the machine learning data available in UCI repository. University of California Irvine is a very famous repository, and they also advertise their KDD archive, knowledge discovery, our data archive. So apart from that, we have these other famous resources like StatLib, Dell. Then these days Kaggle is also there. So and in Kaggle, like because it is like a forum where other people in general also can submit data. So there also we get a lot of data available. But these are like resources wherein the validity of the data and the the consistency, the correctness of the data is heavily checked also. So these are like more standard sources, and like many experiments on ML have been like validated and presented to the world based on data available in these data resources. So some of the other resources from where we can get more information regarding the theory of machine learning. So that I have listed here: the Journal of Machine Learning, research journal, then machine learning journal, IEEE transactions and neural networks, IEEE TPAMI, or transactions and pattern analysis and machine intelligence, panels of statistics, Journal of American Statistical Association. So these are older ones. Some of the popular conferences are International Conferences on Machine Learning, ICML, and then ECML, and then Neural Information Processing System, NIPS, Computational Learning, IJCI, ACMC CARITY for knowledge discovery and data mining, and international IEEE international conferences on data mining, like that. So thank you very much. So if you have some questions or points of discussions, so we can have some discussion. Okay, I think then we can stop here. So okay, we'll continue the next session from 2:30. So we'll have now our formal lunch break. So thank you for your patient hearing. Thank you all.